this is interesting. So one question here is how high this threshold is, and then the other question is how low this overhead can be made in practice or in theory. All right, so let me just give some more examples of what people have done with this kind of thing. So different ingredients. So one is you have to talk about what noise model you're going to worry about, and usually, I mean, so we saw sort of last time on Tuesday, I guess, that there's different kinds of noise, and there's all sorts of kinds of noise that we don't even really understand in these devices. So we're not really sure what the noise is often. And of course, it's hard to simulate a quantum system. So usually what people do is, when we're talking about fault tolerance, when we're trying to simulate fault tolerance or something, we just assume that the noise model is something really simple, like stochastic polynoise, because that we can simulate using Gottesman-Knell. Yeah, that's something we need to worry about. Right, so then we talk about what the quantum error correcting code is that we're going to use, and then just talking about the code is not enough, but you have to talk about how you use the code. So this is what I'm calling the fault tolerance scheme on top of the error correcting code, because the same code can be used in very different ways, and the particular way you use the code is very important, actually. Okay, remark. If you know your noise model well, then you should try to deal with it at the hardware level, like with better calibration or something. Because, yeah, techniques for, so these kinds of threshold theorems and these encoding methods, they work in sort of arbitrary local noise, so they work very generally, but you do have this sort of inherent overhead, like you're blowing up the number of qubits by at least a factor of 5 or something, by a significant constant factor, and that's rather annoying. I mean, because qubits are very expensive. So anything you can do to avoid using fault tolerance schemes is a good idea. This is a paper from Manny Knell from Nature, 2005. So this is an interesting kind of chart. So let me try to explain what this picture is showing us. All right, so the x-axis is the error rate, and in this case, he's parameterizing it by the C0 error rate, and so this is. This gamma it's a probability of a CNOT gate. So he's modeling a CNOT gate like this. A noisy CNOT gate is equal to an ideal CNOT gate. I don't know a good notation for this, so let's write it like that. Followed by a 2-qubit depolarization channel, where the depolarization channel, remember, it applies either IX, IY, IZ, XI, XY, XZ, each of those non-trivial Pauli operators with probably a gamma over 15, because there's 15 2-qubit Pauli operators besides the identity. So that's what this gamma is, and then he defines also like a Hadamard will be the same kind of thing. So the noisy Hadamard, in his noise model, it's equal to an ideal Hadamard, followed by a 1-qubit depolarization channel with probably a gamma prime, where gamma prime, I forget, you have to look at the paper, but it's probably like 1/2 gamma or something. I mean, so it's some nice relationship to gamma, which is just built into his paper. It's probably not super sensitive to how you define it. You just have to define it somewhere. So that means you have one parameter that defines all of the noise rates for all the different kinds of gates. You don't have to do a multi-dimensional plot. Right, so that's one axis. This axis is the overhead, and the way he's measuring the overhead is the number of, he's just counting the number of CNOT gates, the number of physical CNOT gates that you're using per qubit and gate.
Per logical qubit?
Yeah, I guess per logical, maybe per logical CNOT gate or something. He's normalizing it correctly, I guess. Okay, so then what are these other curves? So what are these numbers? 6, 5, 4. I don't know what the numbers are. These numbers. So what these numbers are? This is your the number of logical gates. So if the number of logical gates is 10 to the 3, then your target logical error rate is roughly 1 over 10 to the 3, 10 to the minus 3. And so you need like one level of cone. So for example, if your physical error rate is already below 10 to the minus 3, you don't need any encoding, because you're done.
Mhm.
So the overhead is 0 or 1 or something.
Right.
But as soon as your physical error rate gets around 10 to the minus 3 or higher, then you have to have at least one level of encoding. And so this graph jumps up, and you need this many CNOT gates, 100 CNOT gates or something. Your overhead rate goes up to 100. If your physical error rate is more than this, it looks like there's going to be another level of encoding. It's hard to see here, but I think there's a sort of a corner there. I think that the reason for the corner is because he's doing a different level of concatenation. So he's doing 2 levels of encoding instead of 1. And so the overhead jumps up to 10 to the 4. So instead of 10 squared, now we have 2 levels of encoding, so the overhead is roughly 10 to the 4. And then, yeah, so if the physical error rate gets larger and larger, so then you need more and more levels of encoding, and the overhead just gets higher and higher. But it doesn't, you can't keep on doing this forever, because above the threshold you don't get any improvement no matter how many levels of encoding you use. So you only get improvement if you're below the threshold, and then you use more and more levels of encoding. So that's why this sort of asymptotes up here. And roughly, I think he was showing, I forget what he says in the paper, but I think he has a threshold that's on the order of 3%. But still, I mean, you shouldn't read that and say that 3% is okay. Because if your error rate is, first of all, 3% is not okay, but even if you're below that, even if your error rate is 2.9%, that means you're just like here, and you're almost at the asymptote. So the overhead is astronomical, 10 to the 8, 10 to the 10. I mean, you don't want to be working in that range. You want to be working at well below the threshold, well below the asymptote, so that things are down here. And so that's just this first curve. So these other curves are the same thing, but for different numbers of gates. So here, this is for if we want 10 to the 5 logical gates. So the logical error rate should be 10 to the minus 5. So we don't need any codes here. Here I need 1 level of encoding. Here I need 2 levels of encoding, 3 levels, 4 levels, and it gets bad. It's the same kind of thing. But you see it's scaling quite nicely in this direction. So as the number of logical gates grows, so as the logical error rate decreases, as our target logical error rate decreases, the overhead is not increasing badly.
But it's interesting, like for the 10 to the 5 case, the overhead remains constant pretty much until like it goes past 10 to the negative 4 and it kind of goes up. But for the next case up 10 to the 8, you don't see that same behavior being constant for a while.
Well, I mean, that's because it'll like
it
this
probably
curve
goes that
goes
way,
down
yeah.
to 10 minus 8 probably.
Yeah, okay, right, okay.
Probably the same.
Same, yeah.
Yeah, I don't know. You can probably figure out lots of weird things, like why is it flat and then it sort of goes up smoothly and then it jinks instead of a sharper corner.
Is that because of the log scale?
No, I think it's well, maybe. I think it might be just because it's a post-selection based scheme, so. I think it might come from post-selection, but I'm not sure actually. Yeah. So anyway, if you have a scheme, you can imagine drawing this kind of picture yourself. It probably takes a little work, and then you can look at whatever you want. So you can say, okay, I'm running Shor's algorithm, so I need 10 to 11 gates, and 10 to 11 roughly 10 to 13. That's as close as I have. And so you just look at this at the x-axis, and you can figure out my physical error rate is 10 to the minus 3, and so therefore my overhead is 10 to the 5. Whatever. So that's how you can use this kind of diagram.
So this is only for the post-selection based scheme?
This is only for his particular scheme. Yeah, so every scheme would have its own picture. Yeah. And some schemes would be better in certain regions than others. So like this scheme, this paper, this scheme is interesting because its threshold is extremely high, but it's not so interesting because the overhead is also quite high. So if you start with a low error rate, you probably want to you wouldn't use this scheme at all. You just switch to a different scheme. So that's one of the problems, I guess. Yeah. Okay. Yeah.
So if we already know the parameter gamma, so is there any efficient way to simulate a channel by unit terms, like by circuits?
Well, No, I mean, I'm just saying you can use Gauss-Mixnil. So, in most quantum algorithms, like Shor's algorithm or something, most of the operations are rotations by weird angles. 1-qubit rotations by weird angles, which means that Gauss-Mixnil does not apply because they're not Clifford gates. So you can't simulate them. But that's okay, because when you're actually doing a quantum computation, most of the work is not in running Shor's algorithm. Most of the work is in running the fault tolerance scheme. And in all these fault tolerance schemes, all the gates will be Clifford gates. So actually, even though you can't simulate Shor's algorithm, you can simulate the fault tolerance portion of it efficiently on a classical computer. So you can do this just on like a large, run it on a cluster or something. And, you just run it many times, introducing stochastic poly errors and pushing them through to see what they end up as. But yeah, if you have a non-poly error, then I don't know. We were just talking about this. It becomes hard, I guess.
So,
But did we find there are packages that do this. We were looking at this QLAX. So if you're interested, maybe you should Google this.